Hi, this is Kirsten Findell, and I'm going to speak about land-atmosphere interactions from the perspective of someone who's at a global climate modeling center like GFDL. So many of my studies that I'll discuss are modeling focused, and I hope to share some process level understanding that's applicable to local and regional impacts. So let me just give you a little guide to where I'll go in this talk. I'm going to start by describing the two different legs of land-atmosphere interactions. First, the land leg, which really deals with conditions at the surface and how those control surface flux partitioning. And then the atmospheric leg, which is really how the boundary layer responds to those fluxes from the land surface. I'll give a few different studies, a few different examples of studies that touch on some of these aspects of land-atmosphere interactions, all from this viewpoint of the local coupling perspective or LOCO perspective, which is really in a sense a one-dimensional sort of column view of what goes on at a given location at the land surface influences the column of air above that spot. Then I'd like to move beyond this local coupling vision and talk about surface heterogeneity and the impacts of heterogeneity on boundary layer processes. And finally, I'll end with a little comment on the importance of good long observational records. So let me start by looking at the land leg. And this is really important because moisture availability determines flux partitioning at the ground surface. And the relationship between soil moisture and latent heat flux is highly nonlinear. So where your soil moisture PDF falls in this nonlinear relationship space is very, very important for a number of downstream consequences. The schematic on the right is from a paper that's in review right now by postdoc Suchin Doan, and it breaks up this relationship into four different regions. The first one is below some critical soil moisture threshold. There's essentially not enough moisture available for any real ET to happen. Next, there's a water-limited regime where more moisture means more evapotranspiration. After that, an energy-limited regime where the addition of more soil moisture does not increase latent heat flux because that flux is effectively set by net radiation. And finally, in the wettest part of the domain, there's a rain-dominated regime. Now, of course, the schematic makes it look simple, but in reality, it's much more complicated than that. The figure below, the figure on the bottom right now shows individual days of data from summertime conditions at a grid cell in southwestern Brazil from one of our Earth system models at GFDL. The x-axis in both plots is soil moisture, the y-axis is latent heat. The colors in the plot on the left are the associated daily precip on that day, and the colors on the right are temperature. One thing that I want to draw your eye to is this relationship between the hottest days occurring when the soil moisture is in this transitional or water-limited regime. And that's a very, very important factor that has big consequences when we think about how global warming might lead to a drying of soil moisture, of upper layer level soil moisture, which means a shift of the PDF towards drier conditions. If that PDF shift all happens within this wet regime, then that's not going to have big consequences for temperature. If, however, it means that you're going to push some of your soil moisture PDF into this transitional regime, well, you can see that that could have big implications for temperature. Finally, I just want to point out what this dashed orange line is in our schematic. And what that is for points where bare soil days are produce very different evapotranspiration as later in the season when vegetation may have greened up and root distributions may essentially provide access to soil moisture that's below this upper level. So it adds a little bit more complexity to an already complex relationship. Here's a study that focuses on a comparison between pre-industrial and 4 times CO2 simulations from 7 different CMIP5 models. In the upper plots, it focuses on the mean warming response, where you really see the difference between warming over land than ocean. So the land warms more than the ocean. In addition, we can also see that dry lands tend to warm more than moist lands. This is emphasized in the upper right plot, which is provided with the context of the aridity index. So it shows that the temperature response, the temperature response is most substantial in dry land regions where the aridity index is high. In contrast, if we look at the extremes relative to the mean, we see that in moist or moist land regions of the tropics and the subtropics, the difference between the upper tail of daily mean temperature and the mean of daily maximum temperature, so that the upper tail of the daily maximum temperature, PDF, is substantially amplified in moist land regions, that this is where the response is strongest. And this is a direct consequence of how the PDF of soil moisture in those moist lands, that a substantial portion of it falls in that water-limited regime where temperature effects are most substantial. We can look at the PDFs themselves of daily maximum temperature and see how then the whole PDF responds to an increasing CO2 world, and break it up into these three different regimes. First, a dry land regime, where the entire PDF of temperature is shifted to warmer conditions. Additionally, in the oceanic regime, we also see a shift of the PDF, the full PDF, without much change in the shape. However, in the moist land regime, we see a shift to warmer conditions, but also a change in the shape of the PDF, with substantial warming of extreme hot days, which it really shows up as a lengthening of the hot tail over on this extreme right plot here. That amplification is compounded on top of the general shift to warmer temperatures that we see in the mean of that PDF as well. And the magnitude of that shift is as large as 20% of the global mean warming. So it's a substantial effect that is, again, a direct result of soil moisture limitation. Now let me share a study that really highlights the importance of vegetation cover. So this was a study with our Earth System model ESM2G from GFDL, and I'm comparing a historical simulation to a potential vegetation run. So there, all the forcings are the same as in the historical simulation, except the land use and land cover at the surface is not the historical depiction, but instead it's what we call potential natural vegetation. So it's the vegetation that would be at the land surface if humans had not altered the land surface at all. And here I'm showing the mean temperature and humidity response to what is effectively a deforestation scenario in these altered regions. And it shows that with less forest cover, summertime means are hotter and drier. We can look at this from the perspective of the diurnal cycle as well. So if I take, this is one grid point, these are monthly mean July diurnal cycles from one grid point in one of the heart of that red region from the previous slide. And these are using mixing diagrams. So on the x-axis, we have a humidity term. On the y-axis, a temperature term that are in equivalent energetic units. So these are conserved variable diagrams. And what they show us is that on the crop-covered terrain, we are far more frequently in the hot, dry part of this parameter space than in the forested example, the forested simulations, where almost all of the July monthly mean diurnal cycles remain in the cool and high relative humidity part of this parameter space. If we look at the means of each of these monthly mean diurnal cycles, and we look at them from the context of the moist enthalpy, or the lines of constant moist enthalpy, we can draw these lines at the 90th percentile thresholds for each experiment, and we can see how the historical is different from this potential veg world. We can also look at a measure called the hot-dry measure that is orthogonal to those lines of constant moist enthalpy. And we can look again at how frequently this crop-covered simulation gets into terrain that is it occupies the hot-dry part of this parameter space much more frequently than the potential veg scenario. So if we do that for every grid point, we can see that in the altered regions, what would have been a once-in-a-decade hot, dry summer in the potential vegetation world occurs every 2 to 3 years in the historical simulations. And again, that's just a consequence of change of the land use and change of the vegetation at the land surface. Now let me speak briefly about the atmospheric leg of land-atmosphere interactions. From just a schematic perspective, if we have a very sort of end-member hot, dry landscape or dry or desertified landscape, we have very little moisture available for evaporation. So most of your available energy is consumed by sensible heat flux, which leads to very hot and dry and deep boundary layers. In contrast, over wet or highly vegetated lands, there's a lot of moisture available for evaporation, so very little remains for sensible heat flux. The low buoyancy then provided means that you end up with much more shallow boundary layers, but you're packing a lot of moisture into that shallow boundary layer. So that means that the moist static energy within the boundary layer is going to be very high. If we think of convective triggering as occurring when the level of free convection and the boundary layer top meet, then we can see that in these two end member states, there's very different mechanisms for triggering. Over the dry landscape, we have the boundary layer effectively growing up until it reaches the level of free convection. Whereas over the wet landscape, we have increasing moist static energy within the boundary layer, effectively bringing the level of free convection down until it meets the boundary layer top. This is central to the CTP HI-low framework. So CTP stands for convective triggering potential. HI-low is a low-level humidity deficit index. And fundamental to this framework is the notion that the early morning atmospheric stability and humidity in the area about 100 to 300 millibars above the ground surface, which is the area that the boundary layer is going to grow into and erode, the stability and humidity in that region determine which of these two mechanisms is more efficient at triggering convection. So that framework was applied in this study from a few years ago, where I looked at the sensitivity of the probability of afternoon rainfall to morning time evaporative fraction. And I looked at the expected value of local afternoon rain when it does rain relative to the sensitivity of that term relative to the evaporative fraction. And what this study showed was that flux partitioning at the land surface influences the triggering of convection, but not the amount of rain that falls. But through that influence of triggering of convection, what it was saying was that a higher evaporative flux at the land surface means that there's a higher probability of afternoon rain. So that indicates something of a positive feedback mechanism. So this study, as I said, indicated a positive feedback mechanism. Well, in the same issue of Nature Geoscience, Chris Taylor put forth a study that indicated a negative feedback mechanism. He was looking at spatial gradients of soil moisture, and he showed that convection was preferred at the downwind edge of dry patches. So it was ironic that these appeared in the exact same issue, because they did appear to have some sort of conflict. A few years later, there was a very nice paper that came out and helped to reconcile the different perspectives of the analyses that those two approaches took. And it proved really that these were not incompatible analyses. So Benoit Guillot showed that when you look at from the perspective of from an individual grid point, you look at data over a long time, you see that it rains when conditions are wetter. If you look from the spatial perspective, you see that it rains where conditions are drier. When you bring these two together in a joint perspective, you see that it rains when conditions are wetter and heterogeneous, and then the rain falls in locations which are drier than their neighbors. So we at GFDL right now, and at other institutions too, are working on a climate process team called CLASP, Coupling of Land and Atmospheric Subgrid Parameterizations, that's looking at this in the modeling context. We're trying to, the overarching objective is to get land models and atmospheric models to communicate some of the subgrid heterogeneity that is being captured by each of these independent models, but not communicated. So as part of this, there's definitely parameterization development. And there's also diagnostic efforts to better understand and characterize the important aspects of the surface heterogeneity. So some of that diagnostic effort is being done by postdoc Zunyin, who's looking using ERA5 data right now to look at, from a temporal perspective, things like convective triggering potential, the HI low, and the regimes of feedback that then become that those two metrics help show lead to different kinds of feedback between the land surface and the atmosphere. He's also looking from the spatial perspective at spatial variability among grid points and looking at how soil moisture gradients are correlated with locations of local maximum convection. And there he sees that you get a different sort of map view of what the spatial perspective provides on whether there's a dry soil or a wet soil preference. So these are just some ways to try to characterize what the important aspects of surface heterogeneity are and how we then characterize whether a model is doing a good job in capturing the most important parts of this, this whole messy set of feedbacks between the land surface and the atmosphere. I think, though, what this tells us is surface heterogeneity clearly requires us to move beyond the 1D column view, and the multidimensional nature of this parameter space suggests the need for robust observational efforts to capture examples in all parts of this multidimensional parameter space. That's consistent with a paper that I had a few years ago where I looked at a reanalysis data set to essentially try to answer the question of if I wanted to compare my global model to observational data sets to see if I'm capturing land-atmosphere interactions appropriately, how long does my observational record need to be? And what this shows was if I essentially sampled my data set as if it was a one summer long field experiment, I could get answers that, for one summer might be entirely different from another summer. But of course, if I took 25 years worth of data, any separate 25-year long sample or 25 summer long sample gives an estimate or gives a vision of climatology that is pretty close to all the others. So the upshot of this paper was that if you want to trust the estimate derived from a single observational record, it needs to be a long record. And that data length requirement is particularly important for derived variables. Directly observed variables like precipitation and temperature have a certain parameter space to fill out, and the observational record needs to characterize that. But because metrics of interaction between variables essentially have a broader parameter space to fill out, they need longer records than directly observed variables. So this just really highlights the power of observational data and the power of networks like Ameriflux, and how important and how critical these networks are as vehicles for this sort of long-term data collection. We are hoping that another important aspect of this can be contributed by this vision of the GLAFO, which is a land atmosphere feedback observatories that are supported by the GWEX and GLASS initiatives. They're modeled after the success of the land atmosphere feedback experiment that was a field campaign run at the Southern Great Plains site in August of 2017, spearheaded by Volker Wolfmeyer and Dave Turner. Volker has a poster that he's put together about the GLAFO vision that's here in this Ameriflux workshop, so I hope you'll all visit that and discuss this with Volker. The vision of GLAFO is that it's really characterizing, at a given site, characterizing conditions in the soil, including both soil moisture and temperature, conditions at the land surface, including vegetation and all the characteristics of vegetation, including surface energy balance stations, and then including LiDAR systems that are vertically staring and scanning to capture aspects of turbulence within the boundary layer top, mesoscale vortices, and allow us to capture these processes, sample these processes in field at high resolution temporally and spatially, but also with a dedicated long-term observational focus. So hopefully that is an inspiration. It's certainly an inspiration to me. Volker has a great vision, and I hope we can make it a reality at many different locations around the world. Thank you very much.